Hello students. Let's try something a little different. Suppose we want to take subsets of a collection of distinct objects. So these are distinct: red, orange, yellow, green, and blue. Well, for that we could actually just use the product rule still, right? Because we have two choices for red. We could either include it or not include it. And then we have two choices for orange. Once again, we can either include it or not include it. Two choices for yellow, two choices for green, two choices for blue. And each one of those determines a subset. And notice that my choice of whether or not I include red has no bearing on for whether or not I include orange, right? Or even if it did, it wouldn't have a bearing on the number of choices for whether or not I include orange. So we're allowed to use the product rule here. So I'd get 2 to the 5th. And in general, if I want the number of subsets of, I'll say from instead of, from an n element set, well, that's just going to be 2 to the n. So not very hard at all. But what happens if I now want the number of subsets of size 2? Okay. Well, one thing you could do is you could say, okay, I have to pick 2 elements. So I have to pick one element in 5 ways, and then I have to pick another element in 4 ways. But there's a problem with that. And the problem is not that the first choice changes the number of choices for the second one. The problem is that I'm going to accidentally double count things. Because if I choose red first and then orange, well, that shouldn't be any different than if I choose orange first then red, because I want to choose a subset now, not an ordering. So no order here. So I'd end up counting that twice. Now, you could say, okay, well, what I could do is I know that I'm going to count that exactly twice, and I know for any subset of size 2, I'm going to end up counting it exactly twice. So I could divide by 2 when I'm done. So this would be a method of intentional double counting. Intentional double counting, and this is useful. Double counting is actually a nice technique sometimes. As a matter of fact, it's a very famous technique. But first, let's say how we would solve this problem here. So I want to know the subsets of size 2. Okay, so I want to know the subsets of size 2 from these 5 objects. Well, I know that if I take a first block and a second block, I have 5 ways to choose my first block, 4 ways to choose my second block, but I know that if I use that to count the number of subsets of these blocks, I'll have counted every subset twice, because I'll count twice, once for each possible order. So if I divide by 2, I'm going to get 5 times 2, which is 10. Okay. Another way to think about this is if I wanted subsets, and in this case, it's kind of nice to draw a little picture. Because it's 2, and we're talking about subsets of size 2, whenever you have subsets of size 2, you can draw a graph, a complete graph connecting everything. So here, the vertices, or points, the points are vertices, they represent the colors: red, orange, green, blue, oh, I forgot yellow. Okay, so these represent the colors, and each edge will represent a subset, because every subset contains exactly 2. So I can actually count the edges, and we have 5, and then we have a 5-pointed star. So 5 and 5 is 10. We have 10 edges. This only works for subsets of size 2, though, the whole drawing the complete graph method. But this double counting, neither of these are the method I want to use, by the way. We'll get to a more general method. But I want to focus on double counting. What's another famous example of double counting? Well, maybe the most famous one is the one from the Gauss myth, or the Gauss fable, where supposedly when Gauss was in elementary school, the evil teacher told the students that they had to add up the numbers from 1 to 100, and Gauss immediately wrote it down on his slate. Back in the day, you didn't have fancy tools like pencil and paper. You had your slate and chalk. Gauss wrote it down. He went to the teacher, boom, and he wrote the number 50/50. And the teacher's pulling his hair out, and he's all angry. If you want to learn more about the Gauss myth, and you want to convince yourself that it's a myth that's been passed on and changed over time, Brian Hayes has a wonderful article on that story. But let's just double count. So what did the teacher do? The teacher told the students to add the numbers from 1 to 100, which sounds a little tricky. 98, 99, 100. But the thing is if you double count, if you count every number twice, you can count them one in one direction and one in the other. So you're double counting in order to make your life easy. What do I have? I have 101, and how many times do I have 101? Well, I have 101 100 times. So I have 101 times 100, 10100. But what did I do? I counted each number twice, so I actually have to take that, divide by 2. And that's how I get 50/50. So double counting is a valid strategy. One thing you have to make sure, though, is that you've counted everything twice, or everything 3 times, or everything 4 times. As long as you can confirm that, then you can just divide by the number. And like I said, that can be useful. Let's do another example here. We'll pretend it's a different example. Let's say we want to find the subsets of size 3. So that would be red, orange, yellow, red, orange, green, red, orange, blue, and then we'd have maybe red, yellow, green. I'm already starting to get confused, but I want you to notice something here. If I want to count the subsets of size 3, for any one of those subsets of size 3, I have to leave out a subset of size 2. So by counting the subsets of size 2, for any subset of size 2, I could just take the elements that weren't chosen, and I'll get a subset of size 3. So there's a bijection between the subsets of size 2 and the subsets of size 3, because you can always go from the elements that were included to the elements that weren't included, and vice versa. So I know that if I wanted the number of subsets of size 3, I could just take the number of subsets of size 2, which once again is 10. Okay. But I actually want a formula, a more general formula. These are like what happens if I toss in purple. And now I want the subsets of size 3. Well, I can't use that trick again because the ones that aren't included will also be a subset of size 3. So I need something a little better. So what we want to do is we want to define C and R, or the R combinations, from N, not form, but from N, and that's going to be the number of subsets of size R from a set of size N. I like saying a set because then I don't have to say that the elements are distinct, because otherwise the set wouldn't have size N. Remember, a set knows no repetition. A normal set, there'll be multi-sets too in this, but from a set of size N, just a plain set. So we have N distinguishable objects. We want to choose a subset of size R. And this is much like when you have a hand of cards. You don't care what order you're dealt the hand, usually. In most games, it doesn't matter. You care what the cards are, what's in the subset. So no order. So that's what this counts. C and R, or N choose R, the number of subsets of size R from a set of size N. Let's get a formula for that in the next video.